We may define the task of diagnosis as determining what is wrong with a malfunctioning device, or more generally, what is the fault that is responsible for a malfunctioning system. Given a system, we expect some behavior from it. We expect it to do something. However, we may observe that the system is doing something different. So there is the expected behavior and there is the observed behavior, and there is a discrepancy between them. When there is a discrepancy, we know that the system is malfunctioning. The question then becomes, what is the fault or the set of faults responsible for that malfunctioning system? When we think of diagnosis, we typically think of medical diagnosis. But of course, diagnosis can occur in a very large number of domains. Here are 3 diagnostic domains with which all of us are familiar. The first figure shows the engine of a car. When I insert the key into the ignition system, I expect the engine to turn on. That is the expected behavior. But suppose that I insert the key and the engine doesn't turn on. That's the observed behavior. There is a discrepancy between the expected behavior and the observed behavior. When I insert the key into the ignition, I expect the engine to turn on. That's the expected behavior. But let us suppose that I put the key in and the engine doesn't turn on. That's the observed behavior. There is a discrepancy between the expected behavior, turning the engine on, and the observed behavior, the engine doesn't turn on. So I know there is a malfunction. Given this malfunction, the question becomes, what is the fault or faults responsible for it? And that's the diagnostic task. To address this diagnostic task, I may use a rule which says that if the engine doesn't turn on when the key is inserted, check the carburetor. Suppose I go and check the carburetor and everything is okay with the carburetor. Then another rule may get activated, and that may say, if the engine doesn't turn on and everything is okay with the carburetor, go check the spark plugs. In this way, I may use a production system to isolate the fault or faults responsible for the malfunction.
Something similar happens with computer hardware repair. When we turn on a computer, there are a few behaviors that we expect of it. We expect it to boot up quickly, we expect it to run fast, and we expect it to stay cool. Now imagine if we turn on a computer and notice it started to run at a much higher temperature than we're accustomed to. We might remember that the last time we encountered this problem, the problem was with the fan. So we might use that to then diagnose this as a problem with the fan and replace the fan. This happens at the software level too. If I'm writing a program and the output differs from what I'm expecting, I set about debugging the program and finding the fault. One way of doing that is called rubber duck debugging, which involves explaining my model of how my program works to the rubber duck, so that I might uncover the error by forcing myself through an explanation process.
Note that we discussed the same diagnostic task in 3 different domains. In each domain, there was a discrepancy between the expected and the observed behaviors, and we tried to identify the fault or faults responsible for it. Note also that we alluded to 3 different methods for doing diagnosis: the method of rule-based reasoning, the method of case-based reasoning, and the method of model-based reasoning. We haven't talked a lot about the method of model-based reasoning so far. We will do so when we come to systems thinking later in the class. Of course, we can use the method of rule-based engine not only for diagnosing car engines, but also for repairing computer hardware or for diagnosing computer software. In this particular lesson, our focus will be on the diagnostic task. By now, all of us are already familiar with many reasoning methods that are potentially applicable to the task.